xy equals 2, yeah. So between y is between 1 and 3? And we're going about the y-axis. Okay. So that means we want to write this x equals, probably. So x equals 2 over y. And alternatively, we know that y equals 2 over x. Oops. And so we should make a sketch of this. Let's go over here. All right, so there's my x-axis, there's my y-axis. And we need to get up to 1, 2, 3 that way. Let's go 1, 2, 3 that way. And so this is like the reciprocal function, except we're doubling in each direction. So normally, for example, we would have the point x equals 1, y equals 1, and this 2 says to double that. So we should have the point 1, 2. And for example, we would normally have the point 1/2 goes with 2, and we're doubling that, so 1/2 would go with 4, which would be way up here somewhere off my area. If we come over here and say, well, let's let y equal 3, what happens? Then we see that x would have to be 2/3, right? So 2/3 is about here, y is 3, and that falls right in between those other 2 points I was plotting. And if y equals 1, then x has to be 2, so we get a symmetric point to that one right there. So this right here is the chunk of the curve that we're revolving. And just note about this curve, it continues to climb up asymptotically toward the line x equals 0, and it's going to drop asymptotically toward the line y equals 0 over there. But we're just concerned about that black chunk in the middle, and we're going to revolve that about the y-axis. So rough sketch of that surface is going to be something like a small ring at the top and a bigger ring at the bottom. It is, what, 2 units high, and it heads out 2 units in each direction at the bottom. So it's going to roughly look like this. And we're going to slope down towards those sides. So we're going to build this kind of volcano-looking type shape. Make one of those lines dotted. And then right through the middle here is our y-axis. Okay, so that's what we're trying to create. As far as surface area goes, we go off the surface area of a cone or a frustum, and the surface area of a frustum is the average of the top and bottom radius times little chunks of the Pythagorean theorem. And the calculus version of the Pythagorean theorem, remember, is the square root of 1 plus your derivative squared. Now here, I'm going to have a function of y, right? So we could call this g of y. So I'm going to have 1 plus g prime of y, and that needs to get squared. And then otherwise, since we're revolving, we have circumferences going on, and that's going to be a 2 pi g of y. And here we're integrating y from some value to another value. So this is the general formula for going around the y-axis right there. And what helps me remember it again is this right here is 2 pi r. That gives me my revolving. And then a frustum, or part of a cone, are basically these little triangles that are getting revolved. And that slant edge is a chunk of the Pythagorean theorem. And that's the calculus version of the Pythagorean theorem. So calc Pythagorean theorem, which we also use when we're calculating arc length, right? And this chunk here is our 2 pi r, which gives us a revolution. So we have to revolve our little chunks of the Pythagorean theorem. All right, so for this function, we have our 5-step process. What's step 1 after we've drawn a picture? Take the derivative, yep. So step 1 is to find, in this case, it's x prime. And x prime is going to be the derivative of 2 over y. Oops. And I think I'm going to rewrite that. So instead of calling it 2 over y, let's erase that. I'm going to call it 2 times y to the negative 1. So I need the derivative with respect to y of 2y to the negative 1. What's that derivative? Okay, what do we do? Well, with derivatives, we drop the power, right? With integrals, we raise the power. No, that would be dropping the power. Oh, we're taking the derivative, yes. Sorry, I thought we were taking the integral for a minute. Yeah, okay, so we bring down our negative 1. Thank you, Darren, for keeping me straight. And then we're going to drop that power because we're taking the derivative. So we get that right there. All right, step 2. We're trying to build this right here. We got to square it, yeah, so we need x prime squared. Right, because we're trying to build this thing here. You could write it down all at once, but that doesn't usually work very well. If I square that thing, negative 2 squared is positive 4, and y to the negative 2 to the second is y to the negative 4th. All right, then we add 1 to it. So I'm just going to write 1 plus 4y to the negative 4th. Step 4 is to take its square root. Square root of 1 plus 4y to the negative 4th. And at the moment, I'm looking at that, and I'm like, I'm not really sure what to do with it. Let's see. Let me change some colors here. Let's make that black. Oops, I missed part of it. That's all right. Let's see. What could I do to rewrite this to try and clean it up a bit? I could say that's 1 plus 4 over y to the 4th. And then maybe I could try doing this addition here. So you got to try screwing around with algebra to see if you can clean it up. So 1 would be y to the 4th over y to the 4th, right? Plus 4 over y to the 4th, which gives me y to the 4th plus 4 over y to the 4th. Does that help down here? Oops, I meant that to be black. Let's highlight all of that. I missed. Highlight all of that and make it black. Ooh, black highlighter too. Okay. So if I plug that in here, I'm going to get a big, tall, long square root where I have y to the 4th plus 4 on the top. And I have what, y to the 4th in the bottom. Oops, y to the 4th in the bottom. We have a rule that says you can break a square root on division if both top and bottom are positive. And given our y values here and our 4th power, I think we're all positive. So I could rewrite this as the square root of y to the 4th plus 4 all over, what's the square root of y to the 4th? Y to the 2nd, good, yeah. So that's out of the root now, which is kind of nice. So it kind of looks more complicated, but I did get rid of the negative exponent and I did pull a y out, so that might help. All right, so what have we done so far? We've cleaned up this part. I think we're ready to try plugging into the whole integral and see if we can do any more with it. So I've just calculated, again, this part right there. All right, let's throw it together in one integral. So now we have, switch to black, the integral as y goes from 1 to 3 of 2 pi times our original function. And our original function was 2 over y. 2 over y. And then my Pythagorean theorem part is the square root of y to the 4th plus 4 over y squared. Is that right? And again, we're integrating with respect to y. All right, that cleans up a little bit. Pull out the constants maybe. So what, we have 4 pi integral from y equals 1 to 3. And then I think I'll pull these two together. So I'm going to call that, say, 1 over y cubed times y to the 4th plus 4 in the square root and dy. So whenever you have a function times another function like this, you're praying you can do a substitution. Otherwise, it's going to be really hard to find an antiderivative. So let's see, what might we use for u? And yeah, do the plus 2 to get that out of there. Yeah, anytime we have a plus in a square root, we'd rather have it gone, or a minus. Yeah, so let's try u equals y to the 4th plus 4 and see what happens. What's du then? 4y to the 3rd dy. So let's see, I do have a 4, but this is really a y to the negative 3, not a y to the 3. That's a problem. So no, if you try bringing the y to the 3rd on the other side, then you're mixing y's and u's together, which is a bad idea. You don't want to mix your variables. You want to keep them separate. You can move constants around, but you shouldn't move variables around in the substitution. It usually doesn't go very well. To the best of my knowledge, I think this is a dead end. Well, that's the problem. If we solve this here for dy, then we're going to have y's and u's on the same side, and that's not going to help. Just to check if that works, if I do that, this says dy equals 1 over 4 y to the 3rd times du. And then when I substitute in here, what's going to happen? Well, this part right here becomes the square root of u, right? This dy becomes all of that, 1 over 4y to the 3rd du. I still have this y to the 3rd out there. And the only thing this helps me with is I get to get rid of the 4. But now I have a y to the 6th I don't know what to do with. Okay, so another option to try and get me out of that is to look over here. Now that says y to the 4th plus 4 equals u. I could rewrite it as y to the 4th equals u minus 4. But I really want a y to the 6th, don't I? Isn't that what I have with the combination of these two? So I want this to be the 6th power here. So if I were to take, for example, the 3/2 power of this side, what's 4 times 3/2? 6. So that means I'd have to do the same thing on this side. So, and bottom line is the only way to try and work with some of these is do a whole bunch of algebra till something starts to look like you can take its antiderivative, and we're not there yet. So my claim here is that y to the 6th is equal to u minus 4 to the 3/2, right? So I could get rid of the y to the 6th here. We might be able to clean that up, so let's try it. So we got rid of the 4, so what's left? We still got a pi. We have 1 over y to the 6th when we combine these things, which is going to be 1 over that. So I'm going to have the integral of 1 over u to the negative 4 to the power 3/2 times square root of u du. So we did successfully get rid of all the y's by playing around with both dy and my original substitution. Am I any better off than before? Well, what have I succeeded in? I got the plus out of the inside of the square root and I took it outside. However, didn't I bring the square root back? Yeah. Oh, I do have 2 square roots, but okay, so what does this guy look like? So let's write it again. Let's go to a new page. Pi integral of square root of u over, I could try writing it as u to the let's see, was it u minus 4 cubed square root of that is another way I could write the 3/2 power. Oh, my pen's freaking out. So cleaning that up, as long as both of these are positive. Now, originally things were positive. I'd have to double check that this is positive here, because can u minus 4 end up being negative? Yeah. So let's see, what before we had, let's see, u equals y to the 4th plus 4, right? And y was 1. So if y is 1, then u is going to be 5. What was our other y? Y equals 3. 3 to the 4th power is what? 81. Plus 4 is 85. U is 85. So between 5 and 85, u minus 4 is going to be positive. Right? So yeah, okay, we're still okay. So I can rewrite this as the square root of u over u minus 4 cubed. But problem, antiderivative for this, I think we're worse off than we started. Right? Because to try and do an antiderivative for that, I'm going to have to do another U-substitution with a different variable. So this looks like a dead end. At some point, you got to decide, I don't think this goes any farther. So we took that pretty far, and we don't know what to do with it. Okay, so with our experience with antiderivatives, I don't think we have a way to find an antiderivative for this. Now, the problem said to use a calculator or a computer program. Use technology, yeah. So generally, it'll say try to find an antiderivative or use technology, or sometimes it just says use technology. I always try to find one. We didn't succeed. Oh well. So let's see. What I would plug into my technology would be maybe my reduced version here. I don't think on the other page we have anything better. Nope. Yeah, so I think that guy right there is probably what we're going to plug in. So whip out a TI or GeoGebra or Wolfram Alpha, or what was that other program we tried? Mathway dot something. Yeah, so we got to try one of those to try and evaluate this. So I'm going to give it a shot in GeoGebra. Start. So I am looking at the integral. So you got to find a piece of technology that you're comfortable with. And let's see, what are my constants here? I had a 4 pi, okay. Where'd you go? There you go. So 4 times pi divided by y to the, ooh, it didn't recognize that as pi. Oh, maybe it did. Divided by y to the 3rd, right? Times the SQRT of 1 plus, no, this one was y to the 4th plus 4. Y raised to the 4th plus 4. Ooh, that didn't work out well. Type that right. Oh, and GeoGebra wants x's. I always forget. It's going to yell at me if I try to hit enter. Okay, let's see. 4 pi, 1 over y cubed. Okay, And then boundaries are from 1 to 3. So tab, nope, gotta go to the end. Tab from 1 to 3. GeoGebra says it's about 18.47 if I typed it right. So just to double check that, I had an earlier version which was 1 plus 4y to the negative 4. And that would have been times my original here. So another way I could double check that, new page, is to say I have the integral, oops, wrong color, using my original functions and a not cleaned up version of the square root function. Let's see, y goes from 1 to 3 of 2 pi times 2 over y, my original function, times the square root of 1 plus 4y to the negative 4 dy. So I'm going to type that one in case I made an algebra mistake, which according to Darren, I did not. So integral, are you trying, what kind, you got a TI or cat trying on, Michael? How's it going? Okay. Oh, okay, yeah, something must have gone wrong there. So let's see, this time I'm typing it as 2 times pi times 2 over y times the SQRT of 1 plus 4, oh, and I got to use x's, I keep forgetting, raised to the power negative 4. Change that to an x. And tab starting at 1, ending at 3. GeoGebra says, yep, that's still 18.47. So I typed 2 different algebra versions of my integrands. So the second time I tried typing this one right here in. Are you not getting that number? You got a 218. Okay, good. How's yours going? You getting the same number? Excellent. Ventura, yours is agreeing too? Did you decide on an app to use yet? Yeah, I do have GeoGebra on my phone. Sometimes it's a pain to use because of the keyboard, but I think it usually works for me. I don't have my phone on me though. Another place we could go to type this in is Wolfram Alpha. I guess we'll do another problem and try Wolfram Alpha. All right, do we want to do another one of these or a volume problem? Excellent idea. Let's do a volume problem. Ah, okay, fine. We'll do number 3. Okay, number 3, Ventura, please tell me about number 3. Let me get a new page first. All right. So this is what? We're still in the 6-4 homework. And this is number 3. All right, what do you got? Oops, y-axis. Okay, so this one is going to be harder to draw because of the definition of my function. So in order to draw this, I'm going to have to carry out that integral. Let's see, I need a different color. There you go. All right, so if I want to draw this, which is usually our first step, then I'm going to have to evaluate this integral right here. So I need an antiderivative for cosine. Not yet. Before I take derivatives, I want to draw the surface we're trying to make here. So in order to draw this, I need to see what my function x, because x is a function of y. Oops, y. Not if I take the integral here. So I need you to help me evaluate this integral. What's an antiderivative for the cosine? Sine, yeah. The 3 is hanging out, right? That's a constant. So I'm going to have 3 times the sine of t evaluated from 0 to y. So that's going to give me 3 times the sine of y. What's the sine of 0? So minus 0. All right. So the actual curve is sine of y times 3. We would need to envision that between 0 and pi over 4. So if I say 1, 2, 3 is right here, and then let's go, let's see, that's about 1. Yeah, pi over 4 would probably be about right here on the same scale. Pi over 2 is about here. Oh, I'm going the wrong direction. This is x equals y. So it's x that needs to go up to 3. And y, pi over 2 would be right here. And this one is pi over 4. So I'm graphing a sideways sine function. So let's see, sine starts at 0 and then peaks at pi over 2. And then it bottoms out again at pi. So the peak, instead of at 1, is going to be at 3 and sideways. So this graph heads up, peaks there, and then drops down, and somewhere over here is pi. And I'm concerned about the length of this curve between 0, let's use a different color, 0 and pi over 4, which is about right there. So I'm taking this part of the curve right there. And again, this is the x-axis, and this here is the y-axis. And we're revolving that around the y-axis. So somebody help me out with a calculator. Maybe we don't need a calculator. Let's see. Sine of pi over 4 is square root of 2 over 2. And if I multiply that by square root of 2 over 2 is about what, 1.4? No, 0.7. 0.7 times 3, it's like 2.1. So yeah, that red point is actually over here more. So the point here is my radius across this way is about 2.1. So if I try to sketch this, the radius is about 2 that way and 1, 2 that way. So I'm going to have this circular figure, and then pi over 4, which is a little less than 1. So the peak will be down here, and it arcs over to each side. So this is going to be a cone with a slight point at the bottom and slightly curved sides. Oops, I didn't want to erase that much. So this is my best artistic rendering. And what we're trying to calculate here is how much paint would it take to paint this cone on the outside. Okay, so now that we've drawn it, let's go through our steps. Step 1 here is to find g prime, or x prime, however you want to call it, which is the derivative with respect to x, or y, sorry, wrong variable, of the integral from 0 to y times 3 cosine of t dt. Always draw these. Every time I expect to see a picture to the best of your artistic ability. At the very least, you want this picture right here of the axis of the 2D thing we're trying to revolve. All right, what does the fundamental theorem say about the derivative of an integral? They cancel. It's the integrand, yep, evaluated at the upper boundary. So this is going to be 3 cosine of y. Okay, to take that square, so that's going to be 9 cosine squared of y. Next step, add 1. And then take the square root. And then the last step is to put it all together into your integral. So general form of an integral like this, we're going to integrate here as y goes from 0 to pi over 4. And then we have 2 pi times our function. Now our function, again, is this crazy integral right here, but we reevaluated it over here. So I'm going to have a 3 sine of y. So it turns out I did need to do that. Sine of y. And then times that square root we just found. 1 plus 9 cosine squared of y dy. And aside from the integral, we tried one of these in class yesterday. I think I had just let, and I did y equals cosine of x, I think is the one I did in class. And then we tried to let this right here be our U-substitution, and we've tried 2 different ways and we failed each time, okay? So just to double check that we're gonna fail again, we don't have a technique yet, I'm gonna give it a try anyway. Likely U-substitution is 1 plus 9 cosine squared. So on a new page, if I let u equal 1 plus 9 cosine squared of y, I have to find du. So let's see, derivative of 1 is 0. The 9 is a constant, it gets carried along. What's derivative of the cosine squared? That's 2 functions, so we're going to use the chain rule. Chain rule says take the derivative of the outer function first. Derivative of a square is twice the base. Now we multiply according to the chain rule by the derivative of the base. Derivative of the cosine is, and these are multiplied, is the negative sine of y, and then dy. So altogether, we get a minus 18 cosine of y, sine of y, dy. I put the negative out front here. Yeah, so I said this is positive times negative stuff. Now, cool thing is there is a 9 sine sitting here, and there is a 3 sine sitting there, but do you see a cosine outside of the square root? No, so we're kind of out of luck. Yep. The 1 plus in here is a problem. It's still a problem, but we can try it. Okay, so this is looking like a dead end. Let's go with Darren's suggestion. Oh. So this looks like it doesn't lead anywhere. So Darren said, what if we let u equal 3 sine y? Is that right? Sine of y. Then du is equal to 3 cosine of y dy. All right, so let's see what we can do. Our integral from the other page had us taking y from 0 to pi over 4 of 2 times pi times 3 times sine times the square root of 1 plus 9 cosine squared. Did I get all that right? Okay. All right, so let's see. U is now this thing right here. So problem, we can't have du inside the square root. Although you have a cosine here, it's not in a root, so it doesn't directly relate to what we have here. So although I could say that right there is u, I'm kind of at a loss of what to do with that right there. If we let u be the 9 cosine squared. This is not a perfect square in here, is that what you mean? You could try completing the square on that, but it's going to, anytime you complete the square, you get a something squared here, plus you get something else on the outside. So completing the square on that won't help either. In terms of cleaning up inside here, we could try the Pythagorean identity and see if that helps. So, and we tried that in class yesterday with a simpler version of this, and it basically led us back to this right here, which we threw up our hands on that too. But it's worth trying, you know. So Pythagorean identity says sine squared of y plus cosine squared of y equals 1. And let's see, we have a cosine squared here. So that means the cosine squared of y is equal to 1 minus the sine squared. We are trying to do something with the square root of 1 plus 9 cosine squared. So that means we could replace that with that. So that would give us inside the roots 1 plus 9 times 1 minus sine squared of y. Distributing the 9, I get 1 plus 9 minus 9 sine squared of y. That's all in the root, right? 1 plus 9 is, so I get 10 minus 9 sine squared. So the Pythagorean identity kind of makes it a little bit worse. I traded a 1 for a 10 and a cosine for a sine. Yes, but when we try a U-Substitution, let's try it. If we let U equal 10 minus 9 sine squared of y, it's supposed to be a y, then du is equal to 9 times 2, or 18. I also have a negative. And then times the base, sine of y, times the cosine of y. Notice, does that look familiar? That's exactly the same du, oh, where'd it go? We found right here. Yeah, so a lot of times when you're trying to solve these, you find these different trig tricks and you get back where you started. And that's because all of the identities are inbred. They're all related to one another. And so if you iteratively reply them, like, oh man, I'm back where I started, which is a pain in the butt. And this is not the last time we're going to see that circular pattern. It's going to happen again in chapter 8 when we play with trig functions more. So you could mess around with this later. I got to get to another class in a minute. But what we're going to find is, at the moment, we have no technique to deal with this. Any substitution we try is not going to help. We're just going to keep either doing a circle or getting something more complicated. So like the problem said, use technology to evaluate this right here. So then I would plug it into something like GeoGebra, Wolfram Alpha, the TI, the Casio, anything that can do numerical integration. When we plug this into, anybody remember what we got yesterday when we plugged this, something like this, into Wolfram Alpha? We got the cosh, or the cinch function, right? And the interesting thing, yesterday we ended up with the cinch, the hyperbolic of the sine of, you know, x or y. Let's call it x for now. Now, the definition of the cinch is e to the power whatever plus e to the negative power whatever. So in that case, I have e to the power sine of x plus e to the negative sine of x all over 2. So this is part of the antiderivative. That's kind of nuts. The cosh, yeah. Right, yeah, we haven't, they're not in the, yeah, so in 7.4, the book introduces the cinch and the cosh, so we'll start looking at them there, and then later in chapter 8, we'll use them a little bit further. They take a little bit of getting used to, especially when we have this combination of exponentials and sines all thrown together. We haven't done anything where we took the derivative of something like that in the past. Did you guys remember taking derivatives of things like this last quarter? It could have come up in a chain rule problem maybe, but not often. Yeah. So this is some really crazy chain rule combination thingy, and we just don't have the experience yet to do it. So most of these problems, 2/3 of them, you're going to have to plug it into some kind of computer program. All right, thanks for playing. If you have any questions on the homework, be sure to either email me or hit that Ask Your Instructor button, and I will get back to you.